But that's not the most efficient way of doing it, and it doesn't help if you have to make subsets that are larger than 2. For making subsets that are pairs, that's fine, but we can also slightly modify our method for finding permutations to find the total number of pairs of teams that can be made from a set of 6 teams, and then we can use this method for finding combinations of any number. So once again, we're dealing with options and choices. This is the most efficient way of dealing with combinations. You have to ask yourself, if you have 6 teams and you have to figure out how many games are possible, what you're really asking yourself is how many times do I have to choose and how many options do I have for each choice. You have to choose twice, because if you're figuring out how many games are possible, you have to choose what are the 2 teams that are playing. What's the first team and what's the second team? And then, if you remember, there's 6 possible teams. So if you're picking what the first team is to play and then the second team, you have 6 possible options for team 1. Any of the teams could be that first team playing. You could think of it as home team versus away team. So if you're saying, okay, how many games are possible? There's 6 teams, any of them can be the home team. And then there's, if we pick A to be the home team or to be team 1, we have to ask ourselves, then how many teams are there? How many options are there for team 2? How many teams are there left? There's 5 teams left. If we pick A to be the first team, then there's B, C, D, E, or F for the second team. Now, with the permutations, we would have just multiplied the top ones and gotten 30. But the slight modification to this method for dealing with combinations is that we're going to treat these as fractions. So we're going to multiply not 6 times 5, but 6 over 1 times 5 over 2, which gives us 30 over 2. When you reduce that, that becomes 15. So once again, we get 15 as a result for the number of games possible. So just like before, when we're dealing with combinations, we can think in terms of options and choices. How many times do you have to choose? How many options do you have for each choice? Once you figure that out, you don't multiply just the options. You have to multiply everything, both the options and the choices, treating it as fractions. So let's practice again. How many 3-letter combinations are there of the 7 letters A, B, C, D, E, F, and G? Once again, let's think in terms of options and choices. If we're asking how many 3-letter combinations there are, we have to make 3 choices. We have to pick 3 letters from these 7 that we're given. We're given 7 letters, A, B, C, D, E, F, G, and so we have 7 options for the first choice, 6 options for the second choice, and 5 options for the third choice. We multiply these together as if they were fractions, so we get 7 over 1 times 6 over 2 times 5 over 3, which is 210 over 6, or 35. So there's 35 3-letter combinations that are possible if you have 7 letters to begin with, or 7 letters to choose from. So it's possible to make 35 subsets of a set that has 7 elements in it if each subset has only 3 elements in it. How does this work in a word problem? So let's take a look at the word problem. At a word problem. If 8 people work in an office, and if 4 of those people are to be picked for a promotion, how many different possible groups of 4 people are there? This is a combination question again. We have options and choices. We have to choose 4 people for the promotion. So we have 1 person to choose from, then another, then another, then another. There are 8 people to choose from to begin with. So there's 8 options for the first choice for the promotion. Once that person is picked, there's 7 options for the second choice for the promotion. Once that person is picked, there's 6 options for the third choice for the promotion. And finally, there's 5 options left for the fourth choice for the promotion. We multiply those together as if they were fractions. Now, when you get to big numbers, you can always reduce. So instead of multiplying 8 times 7 times 6 times 5, and then multiplying 2 times 3 times 4, and then reducing, reduce first. So we can get rid of the 2 and the 3 on the bottom, and the 6 up top, and then the 4 on the bottom, and the 8 up top, and replace that with the 2, because we can divide both the 8 and the 4 by 2. So now instead of having those large numbers to deal with, we just have 2 times 7 times 5, which is 70. So there's 70 different possible groups of 4 people if you're picking 4 out of 8. And what about this one? Sam has a list of 9 destinations he would like to visit on his vacation, but he only has time for 3 of them. How many different sets of destinations can he go to on his vacation? Once again, let's think in terms of options and choices. Sam has to make 3 choices because he has only time for 3 places to go on vacation. Poor Sam. So if he has 3 choices, you have to ask yourself, how many options does he have for each choice? Since he has a total of 9 destinations he would like to visit, he has 9 destinations to pick from for his first choice. Once he goes to that one, he has 8 destinations left for the second choice. And once he goes to that one, he has 7 destinations for the third choice. Because this is a combination question. It doesn't matter where he goes first and second or third. What we're asking for is sets. How many different sets of destinations, not permutations. Not how many different trips are there where it matters where you go first and where you go second, but how many different sets there are. This is a combination question, so we're gonna multiply these as if they were fractions. So we have 9 over 1 times 8 over 2 times 7 over 3. We're gonna reduce, and that gets us to 84. So Sam has 84 different sets of destinations he can go to on his vacations if he has 9 destinations to begin with, but only time to visit 3 of them.